continue D block elements. In the D block elements, we will see magnetic properties. We'll see the magnetic properties. We'll say in terms of magnetic moments. Magnetic moment depends on what? That we'll see. Magnetic moment depends on spin and orbital. Spin and orbital. It depends. So magnetic moment depends on spin of electron and orbital movement of electron. So due to spin, we are getting a 4s into s plus 1. Due to orbital, we will have L into L plus 1 square root. Bohr magneton. Unit is Bohr magneton. L is a sum of the azimuthal quantum number values. S is a total spin. S is total spin. Now generally, this orbital contribution of magnetic moment is negligible. So spin contribution of magnetic moment is considerable. Therefore, we will neglect orbital contribution of magnetic moment. We will neglect. Then we will have a magnetic moment due to spin is equal to square root of 4s into s plus 1. S is called total spin. Total spin is equal to number of unpaired electrons by 2. This we will substitute. Then we will get square root of n into n plus 2 Bohr magneton. Square root of n into n plus 2 Bohr magneton. It is magnetic moment due to spin only. Then we can say like this. Okay. Now we will calculate magnetic moment as per this formula, and experimental value we will see. Both we will compare. Now we will take a scandium 3 plus. It is not having unpaired electrons. How? In the sense scandium electronic configuration is argon, no unpaired electrons, so magnetic moment is 0. So next we will take titanium plus 3. Titanium plus 3 configuration is argon 3d1, so one unpaired electron is there. That one you substitute here, so we will get magnetic moment 1.73. It is calculated value. Experimental value is 1.75. So calculated value and experimental value are coinciding. That means this formula we can use. Okay, this formula we can use instead of this. That means orbital contribution is negligible, spin contribution is considerable. That's what we can say here. Next we can take a manganese. We will take manganese plus 2. Will take manganese plus 2 in the sense this configuration is what means argon 3d5. 3d5 in the sense 5 unpaired electrons are there. Therefore unpaired electrons 5 means magnetic moment is 5 point something. So calculated value how much means 5.92. Experimental value is how much means 5.96. Experimental value is coinciding with the calculated value. That means we can use this formula. That's what it indicates. It indicates that orbital contribution is negligible, spin contribution is considerable. That's what it indicates. Okay. So the how to calculate magnetic moment in the sense we can consider spin contribution alone to calculate magnetic moment. Orbital contribution we can neglect. So next we will take a first transition series. That means 3D series we will take. In the 3D series we will take a bivalent ions. We will take in 3D series everything we will take m plus 2 ions. In this one, which is having maximum paramagnetic nature, in the sense Mn plus 2, because it is having highest number of unpaired electrons, that is 5. Rest are not having 5 unpaired electrons, less than 5. Therefore, in 3D series, take all the elements in plus 2 oxidation state. Now, which is having maximum paramagnetic nature means manganese plus 2. Mn plus 2 is having maximum paramagnetic nature. Because Mn plus 2 is having 5 unpaired electrons, rest of the bivalent ions in 3D series is having less than 5 electrons. Okay. Next, Cu2 plus salts will take and Cu plus salts will take. Cu2 plus salts and Cu plus salts. Cu2 plus salts are paramagnetic. Cu plus salts are diamagnetic. Why is it so? Cu plus 2 configuration is argon 3d9. Cu plus configuration is argon 3d10. So 3d9 means one unpaired electron is there, therefore paramagnetic. 3d10 means no unpaired electrons, therefore diamagnetic. Okay. Next, we'll go for the compound. CO H2O 6 times 2 plus complex we will take. CO H2O 6 times 2 plus complex we are taking. In this one, calculated dipole moment. Calculated dipole moment, how much? Calculated magnetic moment, how much means? 3.87 Bohr magneton. Experimental magnetic moment we will see. Experimental magnetic moment, that is 4.4 Bohr magneton for this. Okay. Calculated value and experimental value shows much difference. Therefore, why calculated and experimental value is showing different values for this? That we will see. Now we will take cobalt, we will take its electronic configuration, we will see. It is a argon 3d7 4s2. So CO plus 2. CO plus 2 means argon 3d7 4s0. So 3d7, we will write 7 electrons now in the 5d orbitals. 7 electrons, 1, 2, 3, 4, 5, 6 and 7. 7 electrons we have written. So we are writing a 7 electrons like this. Now how many unpaired electrons are there? Means 3 unpaired electrons are there. Now that in formula we will substitute n into n plus 2 formula. We are substituting 3, we are substituting. So we will get how much? Means 3.87 we will get. So calculated magnetic moment for this CO plus 2 is 3.87 Bohr magneton. Now experimental value 4.4. Why? Why experimental value shows higher than this? What is the reason? We will see formula of magnetic moment. Magnetic moment formula is equal to square root of 4s into s plus 1 plus l into l plus 1. This s is called what? Total spin. That means spin contribution. This tells about spin contribution of magnetic moment. It is L. This L indicates total, that means orbital contribution of magnetic moment. This L indicates orbital contribution of magnetic moment. So in most of the cases, this orbital contribution of magnetic moment is negligible. In most of the cases, orbital contribution of magnetic moment is negligible. So we are neglecting this and we are taking this spin contribution and we are getting this formula, that is square root of n into n plus 2. This formula we are taking and we are calculating. As per that, we got this. Now, experimental magnetic moment is higher than calculated. This indicates that in this case, orbital contribution is considerable. That's why experimental value is greater than calculated value. So in this case, orbital contribution of magnetic moment is considerable. Therefore, we can say that we have to consider orbital contribution of magnetic moment here. That's why calculated value and experimental value are not coinciding, we can say. This is about magnetic properties of d block elements. Next, we will go for complex forming ability of d block elements. We will go complex forming ability of d block elements. Okay. In the transition metal ions, in the d block metal ions forming complexes, d block metal ions, transition metal ions forming many complexes. Why? Because one reason is size of ion is low. Another reason is charge of ion is high. Next one is availability of d orbitals, availability of vacant d orbitals. Because of these reasons, transition metal ions form complexes. Then we'll see catalytic properties. Transition metal ions is used as a catalyst. Why we are using transition metal ions as a catalyst? Because transition metal ions forming variable oxidation states. One reason is transition metal ions can show variable oxidation states. Another reason, transition metal ions form complexes. Therefore, transition metal ions are used as catalyst. Okay, one example we will see for this. One example we are taking, what is that means? I minus with S2O8 2 minus. S2O8 2 minus gives I2 and SO4. I2 and SO4 2 minus. Let us balance this. Here, what is the catalyst means? Fe3 plus is the catalyst. Fe3 plus act as catalyst for this. Okay. So, what is the mechanism here that we will see? First, this Fe3 plus ferric catalyst with I minus gives ferrous and iodine. This ferrous with S2O8 2 minus gives ferric and SO4 2 minus. Ferric and SO4 2 minus. Now we can see that we can see the reaction. So I minus is converting into I2 here. S2O8 2 minus is converting into sulfate. That means how the catalyst is running this reaction, you see. Catalyst making I minus to I2 while catalyst become Fe2 plus. Fe2 plus converting S2O8 2 minus into SO4 2 minus by becoming ferric. So catalyst involving in the chemical reaction again reproducing. That means catalyst here, this catalyst able to show variable oxidation state, therefore it makes the reaction to undergo. Therefore catalyst transition metal ions is acting as catalyst because it is showing variable oxidation states and it is forming complexes. Therefore we can use D block elements as catalyst. Then we will see interstitial compounds. Interstitial compounds in the sense small atoms like hydrogen, carbon, nitrogen are occupying interstitial sites of metal crystal. Then we are getting what in the sense interstitial compounds we are getting. So how to get interstitial compounds? Small atoms like hydrogen, carbon, nitrogen occupying interstitial sites of metal crystal, we will get interstitial compound. Okay. Interstitial compounds are non-stoichiometric. Example for interstitial compounds are TIC, MN4N, MN4N, Fe3H, VH, vanadium, hydrogen, here 0.56. Then titanium, hydrogen, here hydrogen is how much means hydrogen is 1.7. Okay. So what are the characteristics of interstitial compounds that we will see? Characteristics of interstitial compounds. Interstitial compounds have high melting points, higher than pure metals. Suppose TIC melting point is greater than titanium. Next, interstitial compounds are very hard. Then in that interstitial compounds, borates, if you take the borates hardness is like a diamond. That means interstitial compounds are having very high hardness. Then metallic conductivity will be retaining here. This metallic conductivity and this metallic conductivity will be same. These two have same metallic conductivity. So in interstitial compounds, the metallic conductivity will be same like metals. Then interstitial compounds are chemically inert. Next, we will see alloy formation, alloys. Alloys in the sense metals, different metals combined together to give alloys. Non-metals and metals also forming alloys. So, what are the alloys possible that we will see? Alloys possibility. We will take German silver. So we are taking what in the sense German silver we are taking. In the German silver you see copper is there 25 to 50%. 25 to 50% copper is there. 10 to 30% nickel is there, 10 to 30% nickel, 25 to 35% zinc is there. This is German silver. This German silver is used for what, in the sense is used for making spoons, forks, then utensils. Next we'll see another alloy. We'll see next alloy, nichrome. We are going for next alloy, nichrome. Here nickel 60% present. Nichrome contains 60% nickel, 25% iron, 15% chromium. 15% chromium. It is used for what, in the sense resistance wire for electrical furnaces. It is used for making resistance wire for electrical furnaces. Next alloy we will see bell metal. Next alloy, what means bell metal? This bell metal contains 80% copper, 20% tin. 20% tin. It is used for making bells. It is used for making bells. Next we will see gun metal. Next we are taking gun metal. In the gun metal, 88% copper is there. 88% copper. 10% tin. 10% tin. 2% zinc. 2% zinc. 0.5% lead. 0.5% lead is present. It is used for making guns, bearings. It is used for making guns and bearings, we can say. It is used for making guns and bearings, we can say. Next, we will see next alloy is bronze. Next alloy, bronze. Here 75 to 90% copper is present. 25 to 10% tin is present. It is used for making utensils, coins, statues. Next we will see next alloy is brass. Next alloy is brass. It contains 80 to 60% copper, 20 to 40% zinc. 20 to 40% zinc. It is used for machine parts. It is used for making machine parts. Next we will see alloy steels. Steel in the sense mainly iron should be there. Steel in the sense mainly iron should be there, and other substances, other metals should be there. Now nickel steel. Nickel steel contains iron and nickel. Nickel how much means 2.5 to 5% nickel is there. It is used for making cables and guns. For making cables and guns. Okay. Next, manganese steel. Manganese steel. Manganese steel. It contains manganese. How much manganese means 10 to 14% manganese is there. It is used for ball mills. Ball mills and helmets. Ball mills and helmets. In the steel, in the sense and that steel means conformly iron will be there, and another metal. What metal is there? That metal name will be there for steel. Manganese is there means manganese steel. Nickel is there means nickel steel, like this. Next, chrome steel. Next, what means chrome steel? Chrome steel means what metal will be there? Chromium will be there. How much percentage means 5 to 15% chromium is there. 5 to 15% chromium is there. It is used for manufacturing utensils. Razor blades. Then tungsten steel. Tungsten steel means tungsten will be present. How much means 6 to 8%. 6 to 8% tungsten is there. Otherwise, 14 to 20% tungsten will be there. 14 to 20% tungsten will be there. It is used for making what in the sense? It is used for making magnets. It is used for making electric motors. It is used for making electric motors. Okay. So this is about alloy steels. Then railroads we will see. We will take railroads. Railroads. This railroads contains manganese steel. In this, what is the role of this one in the sense? This will have higher hardness. This manganese steel will have higher hardness, and it removes oxygen and sulfur present in the steel. Why we are adding manganese in this railroads manganese steel in the sense? Oxygen sulfur is there in the steel means that will be removed by manganese. So for that case, this manganese steel will be used here. Sorry. Okay. Next, next we will take potassium dichromate salt. We will take that preparation and properties we will see. We are taking potassium dichromate K2Cr2O7. Its preparation we will see. We will take a chromite ore. We will take for this. We will take chromite ore for preparing potassium dichromate. Chromite ore. This chromite ore formula is what in the sense? FeCr2O4. FeCr2O4. FeCr2O4 contains mixed oxide. One is FeO, another one is Cr2O3. To this, sodium carbonate is added. To this, we are adding sodium carbonate, and atmospheric air we are passing. We are fusing this. We are fusing this one. What we are getting in the sense, this chromite ore becomes sodium chromate. Chromite ore becomes sodium chromate. Then ferrous becomes ferric. Ferrous oxide becomes ferric oxide. Then carbonate becomes carbon dioxide. Carbonate becomes carbon dioxide gas. Then this sodium chromate, to this sodium chromate, what is added in the sense? Dilute sulfuric acid solution is added. Dilute sulfuric acid solution is added. What happens means chromate is converting into dichromate. Now you see that in the presence of acid, chromate is converting into dichromate. In the presence of base, dichromate is converting into chromate. Sorry. Then to this sodium dichromate, KCl solution is added. Potassium chloride solution is added. The sodium ion and potassium ion getting exchanged, and we are getting potassium dichromate, K2Cr2O7. Now, potassium dichromate is less soluble in water, therefore it will be crystallized, whereas sodium dichromate is more soluble in water. Okay. So, to prepare potassium dichromate, we are taking chromite ore. Chromite ore is treated with sodium carbonate and potassium. This chromite ore mixed and melted. Then oxygen is passed, air is passed. This chromite ore, chromium becoming sodium chromate, ferrous oxide becoming ferric oxide, carbonate becomes carbon dioxide. Then to this dilute sulfuric acid solution is added. Sodium chromate is becoming sodium dichromate. Then potassium chloride solution is added into this. We are getting what in the sense? Potassium dichromate. This on crystallization, we are getting potassium dichromate crystals. Okay. So here this point you remember that here chromate is converted into dichromate by adding acid. This acid converts this chromate into dichromate. So dichromate into chromate means you add base. So on adding base, what dichromate is converting into chromate, we can say, sir. Then we will see structures of chromate and dichromate structures we will see, sir. Chromate in the sense CrO4 2 minus. That 2 minus we will split and give -1 here we will give. Now see that -1, oxygen carrying -1 means it will make single bond only. Oxygen can make double bond, otherwise 2 single bonds. Okay. Chromium group number is 6b, so this valence shell contains 6 electrons, therefore it can make 6 bonds. Okay, dichromate will take, dichromate contains 1 oxygen, 2 chromium atoms and 6 oxygen. 6 oxygens we will divide 3 equally and we will give to each chromium. So 7 oxygens we have distributed. So for this chromium 3 oxygens we have given, for this chromium 3 oxygens we have given, remaining 1 oxygen center we have given for both chromiums. This oxygen makes 2 bonds, 1 bond with this chromium, 1 bond with this chromium. This oxygen is having 2 lone pairs, therefore here bent shape. This oxygen makes a double bond. Chromium makes totally how many bonds? In the sense 6 bonds. So one bond we will remove here. And dichromate means Cr2O7 2 minus. So 2 minus, here -1 will give, here -1 will give. It is dichromate ion, we can say. Now you see that all these bonds will have same bond length in resonance hybrid. These 2 bonds will have same bond length. Therefore, in this dichromate, CRO bond length means 2 possibilities there. One is this. All these have same bond length, and these 2 will have another bond length. This bond length is one value. This bond length will have another value. Therefore, 2 bond lengths possible for this dichromate anion. Okay. Next we will see potassium dichromate and sodium dichromate. We will see. Now this sodium dichromate cannot be used as primary standard in the volumetric analysis, whereas potassium dichromate is used as primary standard in the volumetric analysis. So we are saying that potassium dichromate is used as primary standard in volumetric analysis, whereas sodium dichromate is not used as primary standard in volumetric analysis. Why? What is primary standard? Primary standard means what? Primary standard means its concentration is known. Its concentration is known. Now this concentration is known, so we will take this for volumetric analysis. Suppose we are taking this one in burette, then pipette solution we will take in the conical flask. We will titrate. We will find a concentration of another solution. So this solution concentration we know. Using this solution we will titrate. During titration, after the titration, we will find the concentration of another solution. Okay, titration means 2 solutions will be there. One is burette solution, another one is pipette solution. This burette solution concentration is known. Pipette solution concentration we will find it using the formula V1 M1 by N1 is equal to V2 M2 by N2. Using this formula we can find it. Okay, so this potassium dichromate is primary standard, therefore this concentration is known. Sodium dichromate is not primary standard because this concentration is unknown. This concentration is unknown. Why? Because this sodium dichromate is hygroscopic, whereas potassium dichromate is not hygroscopic. Hygroscopic means what? It will absorb water from atmosphere. It will not absorb water from atmosphere. Since it is absorbing water from atmosphere, this concentration is going on changing. It is not absorbing water from atmosphere. This concentration is not changing. It is fixed. So you prepare this potassium dichromate solution. How to prepare? In the sense, take known weight of potassium dichromate, take known weight of water, mix and prepare solution. You know how much potassium dichromate you have taken, how much volume of water you have taken, you know. Then you can calculate concentration. Therefore, concentration of potassium dichromate is known. And this potassium dichromate concentration is not changing due to atmospheric moisture. But sodium dichromate concentration changes due to atmospheric moisture. Therefore, it is not used as primary standard in volumetric analysis, but potassium dichromate we can use as primary standard in volumetric analysis. Okay. Next, we'll see chemical properties of potassium dichromate. Potassium dichromate contains dichromate anion. Here, chromium oxidation number is +6. Chromium can show maximum +6 oxidation number. Therefore, only possibility it can undergo reduction. Therefore, it can act as oxidizing agent but not reducing agent. Okay. Now, in the oxidizing, this dichromate is acting as oxidizing agent. Therefore, dichromate is converting into Cr+3. It is undergoing reduction, while I- is undergoing oxidation in the presence of acidic medium. So I- on oxidation gives I2, dichromate on reduction gives Cr3+. Okay. Then hydrogen sulfide is converting into sulfur. Stannous is converting into stannic. Ferrous is converting into ferric. Ferrous is converting into ferric. Then sulfite is converting into sulfate. Then oxalic acid is converting into carbon dioxide. Oxalic acid is converting into what? Carbon dioxide. Okay. So dichromate can act as an oxidizing agent. That means itself undergoes a reduction. In the presence of acidic medium, it is reducing to give Cr3+. This dichromate oxidizes I- into I2, hydrogen sulfide into sulfur, stannous into stannic, ferrous into ferric, sulfite into sulfate, oxalic acid into carbon dioxide. Okay. Next, we will go for potassium permanganate. Preparation of potassium permanganate we will see. Now, we will take manganese dioxide MnO2. To this, we will add potassium hydroxide, solid potassium hydroxide. We will fuse these two, melting these two. Then air is passed into this. Air is passed into this. What we are getting means potassium manganate. We are getting manganate. We are getting manganate. Okay, we are getting manganate. This manganate undergoes disproportionation. Manganate means MnO4 2-. It undergoes disproportionation in acidic medium or in neutral medium. It is going for disproportionation in acidic medium or in neutral medium to give what in the sense permanganate and MnO2. Now you see that it is +6 oxidation number becoming +7 oxidation number, that is called oxidation. +6 becomes +4 oxidation number, that is called reduction. So disproportionation is possible here. Disproportionation is possible. So this manganate on disproportionation gives a permanganate. Otherwise, this manganate is taken for electrolysis. Manganate is taken for electrolysis in alkaline medium, while it gives a permanganate. It gives permanganate. This manganate on oxidation in alkaline medium, that means during electrolysis at anode, becomes what in the sense permanganate we can say. So in this way permanganate will be prepared. Sorry. Laboratory preparation of permanganate will see. In the laboratory, Mn+2 is taken. Mn+2 to this S2OA 2- is taken. Here peroxy linkage is there. Now Mn+2 undergoes oxidation and gives MnO4-. This S2OA 2- undergoes reduction to give SO4 2- we can say. Sorry. Now we will see permanganate and manganate structures. We will see this permanganate contains manganese and 4 oxygens. That 4 oxygens will write. Then here minus charge is there, that will give to oxygen. This oxygen makes single bond. Rest of the oxygens makes a double bond. Manganese comes under 7B group. Therefore, it can make 7 bonds. Okay. Then we will see manganate MnO4 2- we will see. In the manganate, manganese is there and 4 oxygens are there. Those 4 oxygens will write. -2 will split as -1 -1. Then we can say that here one lone electron will be there. Here double bond, here double bond, here single bond, here single bond we can give. Here manganese oxidation number is what means +6. Therefore, it contains one lone electron. It is manganate. We can say manganate is having green color. Permanganate is having purple color. This permanganate is what means tetrahedral. Here all the pi bonds are d pi p pi bonds. Okay. Next we will see Chemical properties of potassium permanganate. This potassium permanganate solubility in water is very low. Potassium permanganate solubility in water is very low. Then how potassium permanganate solution will be given for a volumetric analysis? In the volumetric analysis, potassium permanganate will be given for titration. How they are giving this potassium permanganate means, first they will take a potassium permanganate in the beaker. Potassium permanganate will be taken in the beaker. Potassium permanganate crystals will be taken in the beaker. To this they will add water. How much water we want to add, that water they will take in the another vessel. Suppose potassium permanganate we are taking x gram. Water they will how much water means, suppose 4 liters of water means take 4 liters of water separately. From this add some amount of water into this. Then using glass rod stir the contents very well. Then transfer the solution part alone. Keep undissolved potassium permanganate here only. Then add some more. That solution you add into another vessel. Don't add into this vessel. This water some more add into this. Stir the contents very well. Then dissolved solution part alone decant into already collected solution. Undissolved KMnO4 will be there here only. Like this, you continue adding water and still collect the solution. Like this, you do it till all the KMnO4 is dissolved. Okay. Why we have to do like this? In the sense, KMnO4 solubility is very low. Therefore, KMnO4 we have to dissolve very carefully like this. Just taking KMnO4 crystals and adding directly into the required quantity of water, if you add, in the sense, what will happen means, some KMnO4 without dissolving it will be settled down. Therefore, KMnO4 solution preparation means like this only we have to prepare. Sir. Chemical properties of KMnO4 we will see. In the KMnO4, permanganate is there. In the permanganate, manganese oxidation number is +7. Manganese comes under 7b group, so it can show maximum oxidation number +7. That maximum oxidation number permanganate manganese is having. Therefore, permanganate can undergo only reduction. So permanganate can act as only oxidizing agent. Permanganate can act as only oxidizing agent. Sir. So now how it is acting as oxidizing agent, that we will see. Now oxidizing agent means it will undergo reduction. So permanganate we are taking. In acidic medium, it is converting into Mn+2. In acidic medium, it is converting into Mn+2. For this standard potential, how much? In the sense 1.52 volt. Then in neutral medium, it is converting into MnO2. In neutral medium, it is converting into MnO2. Here potential is how much? In the sense 1.69 volt. 1.69 volt. In alkaline medium, basic medium, strongly basic medium, it is converting into manganate MnO4 2 minus. For this E0 value is 0.56 volt. 0.56 volt. This is possible under strongly basic medium, strongly alkaline medium. This is possible in neutral medium and weakly basic medium. Weakly basic medium. Therefore, acidic medium means permanganate is converting into Mn+2. Okay. Now we will balance. Here 4 oxygens are there. Therefore, you write 4 water molecules this side and 8 H plus ions this side. Okay. Therefore, we will write 4 water molecules here and 8 H plus ions here and 5 electrons. Okay. It is acidic medium. It is strongly basic medium. Here we will write 1 electron. It is strongly basic medium. It is neutral medium or slightly basic medium. Here we will write 2 water molecules here. Then 4 hydrogens, we will write it as 4H plus. We are writing H plus, therefore it is acidic medium. Don't think that it is neutral medium and slightly basic medium it is. Okay. Then for balancing, we'll write 3 electrons. Okay. Therefore, E0 values we have given here like this. So permanganate is converting into Mn+2 in acidic medium. Permanganate is converting into MnO2 in slightly basic medium and neutral medium. Permanganate is converting into manganate in a strongly basic medium, we can say. Then we'll see oxidizing reactions. Oxidizing nature of permanganate, we'll see. This permanganate in acidic medium means permanganate will convert into Mn+2. This permanganate oxidizes I minus to I2, I minus into I2 in acidic medium. Then ferrous into ferric. It converts ferrous into ferric in acidic medium. It converts oxalate into carbon dioxide in acidic medium. It converts hydrogen sulfide into sulfur in acidic medium. It converts sulfite into sulfate in acidic medium. Okay. Now we will take neutral or weakly basic medium we will take. In neutral or weakly basic medium, I minus is converted into iodate. In acidic medium, I minus is converted into iodine. In neutral medium or weakly basic medium, I minus is converted into iodate. This thiosulfate S2O3 2 minus is converted into sulfate. Then Mn plus 2. Mn plus 2 is converted into MnO2. Here catalyst is what in the sense zinc oxide act as catalyst or zinc sulfate act as catalyst. In these cases, permanganate is converted into MnO2. Like this we can say. Next reaction we'll see. Now we will take potassium permanganate in oxalic acid in the concentrated sulfuric acid solution. Let us take potassium permanganate in the concentrated sulfuric acid solution. This K plus and H plus will be replaced. Therefore, we are getting what in the sense H to HMnO4 we will get. This HMnO4 on dehydration gives Mn2O7. Mn2O7 we will get. This Mn2O7 explodes to give what in the sense MnO2 and O2. This Mn2O7 explodes to give MnO2 and O2 we can say. Then potassium permanganate it is used for as a bleaching agent. It bleaches cotton, silk and other textile fibers. It is used for decolorizing oils. So potassium permanganate is used for what in the sense it is used as a bleaching agent. It bleaches wool, cotton, silk and other textile fibers, and it is used for decolorizing oils we can say. Let us continue in next class.